day. In this session, we have two invited speakers from South Korea and from Sweden. We have 30 minutes of presentation and followed by 15 minutes of discussion. We have timekeeper. The timekeeper will shown in screen, and later he will remind how many time left. Not for long. For the first presentation, we will be hearing a presentation from Dr. Muhammad Hilmi Al-Faruqi from Chonnam University, and who will be speaking to us on emerging post-lithium batteries opportunities in Indonesia. For a brief description of Dr. Hilmi, he is now serving as postdoctoral research fellow in Next Generation Battery Laboratory, Chonnam National University, South Korea. He is also a faculty staff of Universitas Teknologi Sumbawa in Indonesia. He has published so many academic publications, and the publication have been cited for more than 3,000 times. So that in 2020, he has been awarded as the top 15 Indonesian Science and Technology Index. His research interest is material research and development for energy storage application. Let's give the floor to Dr. Al-Faruqi. For Dr. Al-Faruqi, the floor is yours, please.
Okay, thank you very much, Dr. Anata, for very nice introduction. Honorable Dean of Faculty of Engineering, Dr. Salihin Hasla, keynote and invited speakers, organizing committees, professors of ICIMECE 2021. Assalamualaikum warahmatullahi wabarakatuh. Good afternoon. I hope you are all in good condition during this pandemic. And hello for all the participants. First and foremost, I would like to send my deepest gratitude to the committee for inviting me. It is a great honor to be here to share, to exchange ideas. As Dr. Anata mentioned, our talk will be emerging post-lithium batteries opportunities in Indonesia. I would like to share my screen. Okay, can you see my screen?
Yes, it's clear enough.
Okay. Okay, yes, Dr. Anata mentioned, my name is Muhammad Hilmi Al-Faruqi. I'm currently a postdoctoral research fellow at Chonnam National University in the Next Generation Batteries Laboratory, South Korea. And also, I'm a lecturer at the Sumbawa University of Technology. I would like to begin by introducing briefly our laboratory led by Professor Kim Jacob. He was also a student from Professor Mantiram and Professor Gutinap, who was awarded the Nobel Prize in Chemistry 2019. So basically, our lab has many collaboration inside Korea and also in the US and Europe. And we have also collaboration with some big company, for example, Samsung or LG Chem. And basically, besides, of course, besides lithium-ion batteries, this is our work. We also are working intensively on sodium-ion batteries, potassium-ion batteries, as well as zinc-ion batteries and hybrid batteries. So basically, I will introduce and I will share our results on these systems, and let's see what kind of the opportunity Indonesia has for developing this emerging post-lithium battery system. Okay, before we go discuss detail about this emerging post-lithium batteries, there's one very interesting event actually this year. This is the launch of sodium-ion batteries by CATL, Contemporary Ampere Technology Limited. This is one of the biggest battery companies from China. They launched the sodium-ion battery. Okay, this year in July, on July 29th to 2021 this year. Okay. So it's very interesting. This is a very big company. They supply battery for Tesla. Okay, this is they supply battery for Tesla, and now they move also to sodium-ion battery. Of course, this is not the first company who built uh, uh, which built the sodium-ion battery. Like for example, in UK-based company, for example, the Faradion, they also developed the sodium-ion batteries. But this is also another breakthrough because they claim this technology is the highest energy density for sodium-ion battery. So this is just July of this year. It's very interesting. Okay. Uh, as we understand about lithium-ion battery technology that we currently use, for example, from smartphone or from electric vehicles, there are several materials we can use. For example, the LCO, lithium cobalt oxide, the LMO, lithium Mn2O4 manganese spinel, NCA, the combination between the nickel, cobalt, and aluminum, and also the NCM technology, nickel, cobalt, manganese. So we know about this technology. So why we basically also think about what is the next technology that we can use, how we can utilize another elements from periodic table, for example. Basically, if we take a detailed look about lithium-ion battery technology, now we are reached already. This is some of the specific energy-based lithium chemistry. People trying to improve the specific energy of this lithium-ion battery technology. So basically, if we use graphite and with the NCM cathode, for example, it can reach like 250 watt-hour per kilogram. And now people trying to increase the energy density. And this is the Battery 500 consortium in the US. Yeah, they developed the lithium metal NCM. So basically, it has some limitation. Yeah, it has some limitation, and people move from lithium-ion battery to other lithium-based battery, for example, using lithium metal. Okay, we return back to the origin of the development of lithium batteries in 1976, for example, from Professor Stanley Whittingham. And also, some people also move to lithium metal sulfur, yeah, to increase the specific energy. And based on this kind of situation, we need to also understand there is some limitation, yeah, some limitation of the lithium-ion battery technology that we have now. For example, the NCA, NCM, NCA, LFP, LMO, and LTO. Yeah, we can see here even the safety. There's some issues there. Yeah, and also about the cost. Also, yeah, we need to concern about the cost. So if we take a look at these diagrams, this spider web, we can think of new battery chemistry that can be cheaper, and it can be more safety and also environmentally denied. So we move to the emerging post-lithium-ion batteries. But basically, if we take a look at the battery research and development, normally we think we consider about the synthesis and characterization of the materials, and then the performance improvement. And also, we need to we need to discover new materials, especially for this post-lithium-ion batteries. Yeah, even in lithium-ion batteries, we also consider many recipe to improve the performance of lithium-ion battery technology. So basically, of course, for post-lithium-ion batteries, we also consider about all of these things from synthesis and characterization, performance improvement, and also new material. So here, I would like to show you, I would like to share to you some showcase about various post-lithium batteries technology that we have developed in our lab. Okay. So the first one, this is the, basically this is the sodium chromium oxide, yeah. So of course, before that, NCO, or we can say like C here, the C here is chromium, yeah, not cobalt. So this is cobalt-free materials. We try to develop the new cathode, yeah, for sodium-ion batteries. Initially from NCO, because NCO also have some limitation. So we do several strategy to improve the performance. Basically, there's two things that we can do. For example, how to improve the electrical conductivity of the batteries, and second thing is how to improve the ionic diffusion. Yeah. So based on this situation, So we perform some theoretical calculation, for example, using density functional theory, and we vary some ionics. Here, for example, we add here calcium and also titanium. So we perform some structural characterization, and we can see that the enlargement of the c-axis of this cathode. Okay, and then when we perform also some density of states calculation, we can see the improvement of these electronic conductivities of this material. So we expect that after we add other elements, for example, calcium and titanium, it can enhance the electrochemical properties of the battery. And this is the electrochemical performance for both cathodes. We can see here that the superiority of the after the addition of the calcium and titanium is very have some superior electrochemical performance here. As you can see here, for example, from the discharge chart curve and also the C-rate performance, as well as the cyclability, indeed it's show very significant improvement. Yeah, as well as in the lithium-ion battery technology. Also, for example, we know some cathode materials, let's say lithium cobalt oxide or lithium manganese oxide, yeah, or the NCA or NCM. Normally, if we use that one purely like that, the performance still very low and need to be improved. Yeah, that's why some additional elements, additional ions, or even we can create some vacancy. Yeah, it can improve the performance of the cathode materials as well as the performance of the overall battery. Okay, this is the first one, and then we tested also with the pouch cell. Here we use the hard carbon as the anode, and also the NCCTO cathode. And this is very practical, and we can see here how it can improve the performance of this sodium chromium oxide based cathode material for sodium ion batteries. Yeah, of course, still a lot of room. Yeah, can be need some improvement for this performance, but it's kind of a good breakthrough also for the field of sodium ion batteries. So this is the first one. It has very potential. Yeah, normally if we talk about the post lithium ion batteries, we need to understand. Yeah, of course, the weight and the size of this element. Yeah, bigger than lithium ion. Yeah, because lithium ion is the lightest. This is the also the voltage potential also very negative compared to the other elements. So the energy density is very high. But when it comes to safety and the abundance of the elements, that as well as the cost production, so we need to consider this post lithium batteries, and it will be a big push. Yeah, it will be a great push for clean energy. Yeah, for example, solar cell, solar or wind energy, because the cost of the storage is the main concern. Yeah, and the size, the weight of the batteries is not a problem. Yeah, because we will put this one, yeah, in the field. Yeah, in the yard. Yeah, not for portable application, for example. And as I mentioned before in the early presentation, the CATL, the Chinese battery company, when they develop sodium ion battery, so they combine both technology, sodium ion and lithium ion, even for electric vehicle. Yeah, so this can be also interesting breakthrough that hopefully for the next generation battery can find their place even in many applications. Okay, this is the first one, and the other one we also developed these materials, yeah, K0.3 and 0.9 Cu 0.1 O2 technology. Well, we call it as KMCO. Yeah, this is for potassium ion batteries. So basically, we perform this research. Yeah, we include some other technologies, for example, machine learning and also DFT calculation before we validate using experimental characterization. So we also consider here, for example, in this, basically this is manganese based, yeah, manganese oxide based cathode for potassium ion battery, but it also has some limitation, especially when they expose to open air. Yeah, we cannot store outside, yeah, because of this kind of highly favorable thermodynamic reaction. It can shows it can form some other phase, for example, like that. So we, based on our studies, using machine learning and density calculation, we found that after the addition of copper, it's also very cheap element. We add copper into this host materials. So we observe some very interesting results. For example, after we expose to the air, when we cycle the battery, the performance is still very good. It's still very nice. And also the cyclability of this cathode is still powerful, performance compared to the pure KMO, potassium manganese oxide. And the other thing, the other technology for post-lithium batteries that we do, for example, here we have hybrid sodium and zinc ion technology. So basically, this is an aqueous system. This is water-based battery. We use the electrolyte from DI water, and we use zinc metal, it's sort of cheap element, compared to, of course, to lithium, zinc metal anode, and then for the electrolyte, the ions, we use sodium ions and also zinc ions from acetate beds, for example, sodium acetate and zinc acetate. And for the cathode, we use this NVP, sodium vanadium phosphate. This is also very promising cathode materials for sodium-ion batteries. So we synthesize these materials using our techniques. We call it pyrosynthesis. So our group is also prominent for this kind of technique to synthesize, to develop materials using combustion. We can add precursor and mix with the polyol solution, and then we can just ignite it and then burn. And within few seconds, and the reaction happen, and then we can further treat it using heat treatment, for example. And since also we use carbon source, the materials also will be wrapped by the carbon coating there. This is to improve the electrical properties of the cathode materials also. And we have also several patents for this pyrosynthesis technology. So based on this, we developed NVP first, NVP cathode materials, and then we implement these cathode materials in a hybrid sodium zinc system. So if you can see here the schematics, as I mentioned also before, this is the zinc metal, and then this is the NVP cathode, okay, and then inside for the electrolyte we have sodium and zinc ion mixed together, okay. So when we operate the batteries, basically only sodium will intercalate, and they intercalate from this NVP host structure. Okay, and while this zinc, it will be deposited on the and also will be dissolved to and from the zinc metal. Okay. So with this kind of cell configuration, so we test the electrical performance. We can see here even the during discharge and charge. We can see these two plateaus. The first first during discharge and during charge. This indicates the two-phase reaction, and then in the next slide I will discuss a little bit about that. And we can see the performance even at very high rate. It shows still considerable performance, and also for the cyclability test also. Actually, we have tests until the 1,000 cycles also for this system. And we perform in situ synchrotron XRD, when we operate the battery, we test it in situ, so we can see the phase transformation during charging and discharging. As we can see here, we can only observe like two phases. This is two-phase reaction, the Na-Fe2-PO43 and also Na3-Fe2-PO43. So basically, sodium in this kind of system fastly intercalates from the host structure and contribute well for the overall electrochemical performance. Okay, and the opportunities in Indonesia. This is also very interesting. Maybe all of you or some of you have heard the news that Indonesia now invested so many, many infrastructures, many mineral resources here, and then they invited foreign investors. For example, they recently they made an MOU within the LG Chem or LG Energy Solution, and also the Hyundai, for example. And it is basically the supply chain distribution, yeah, for the development of lithium-ion batteries for um, electric vehicle, for example. Yeah. So from material processing, component production, cell production, module production, pack assembly, until the vehicle integration, recycling, or second life, here in Korea, we have all of this. Yeah, we start from material processing, the all big battery companies, and also the automotive company here we have. And if you can see here, this is opportunity from Indonesia. Yeah, Indonesia has many resources about what I mentioned before, the transition metal for cathode material, for example. We have nickel, manganese, yeah, many mineral resources in Indonesia have. But the problem is now Indonesia, for this kind of workforce opportunity, it must be developed, or Indonesia still has no plan yet how to involve to this supply chain of this lithium-ion battery technology. So what I can show you here, for example, let's say take some case from Argonne National Laboratory. So this is very long journey, okay, very long journey from the invented of the NCM materials before they have they give the license, for example, to Valves and to the Kogyo, and then finally the Chevrolet, yeah, and finally they have Bolt EV in 2017, for example, using this NCM technology. And also, if you know Tesla, for example, they have the battery also from the CATL, yeah, some also from Panasonic and also LG Chem. They have very mature technology, yeah. And Indonesia basically has this kind of opportunity, yeah, to involve in this battery production, yeah, from material processing, component production, yeah, as well as to develop until vehicle integration and recycling the batteries. Okay, so I think the government should consider, yeah, this is the good time, because now many scientists in Indonesia, and also even the many provinces in Indonesia, they have shown the prototype of this battery technology with, for example, in the motorcycles. Yeah. So this is also good time. Yeah, this is good time that Indonesia has this kind of atmosphere, yeah, to develop the battery ecosystem. Now it is also good time to start moving also, yeah, to start the research in the post lithium batteries. Yeah, just like the Faradion and the CATL. Yeah, that company, the company, they shifted. Yeah, they shifted already to build the post lithium ion batteries. Yeah. And the reason, the promising one, yeah, still this is sodium ion batteries, yeah, that we can develop. And Indonesia has many has good big opportunity to reach that, become a good player for that. And so my some suggestion, yeah, first, research and collaboration between companies and universities in Indonesia should be developed. Also, we need to have kind of good database also, which company produce what kind of technology, and university also can hire the scientists, yeah, from universities, yeah, just like Tesla. If you know how Tesla developed materials, they work with, for example, Professor Jeff Dunn from Dalhousie University, for example. So that kind of collaboration should be there, yeah, if Indonesia wants to reach that milestone. Yeah, we cannot work like separately like this. Okay, and we should establish the research lab, battery testing, and material characterization instrument. It's very important. Yeah, and also we need to introduce the lectures on batteries. This is also very good for the next generation, so they know some recent updates about battery technology, about the material processing, until the how it can be used in electric vehicle or something like that. Yeah. So basically, government should encourage diverse research topics, not only lithium batteries, yeah, but also another battery technologies, including sodium-ion batteries. Yeah. And don't forget also, I think growing local automotive companies, it will be a very good step also to establish this kind of ecosystem. Okay, and finally, before we finish this presentation and we have maybe some discussion, we can share ideas, we can exchange some knowledge. Some concluding remarks from me. Of course, Indonesia, if you can see here, Indonesia mining map, many mineral resources. So we need to optimize, we need to optimize this minerals, and then we need to think, of course, second one, to increase more the number of scientists and researchers, and to work on many aspects from mineral processing, until the production of the batteries, and also filing more and more intellectual properties. This is also very important, and moving to new technologies, for example, post-lithium batteries, sodium or potassium, or even zinc or hybrid, the water-based aqueous technology. This is also very good opportunity for Indonesia. And lastly, people, the battery researchers, and also they move to use cobalt-free materials. So they now improve the performance of nickel-based, manganese-based, nickel-rich or iron-rich, even vanadium and chromium element-based cathode materials. So basically, cobalt, they try to reduce or remove cobalt at all from the structure. So Indonesia, it can be a good chance. Once again, for example, we have a lot of manganese resources, nickel. So this is the direction from the government, how they can manage the Indonesian researchers, scientists. I understand there are a lot of Indonesian battery right now, and battery scientists, battery researchers. For example, even at the UNS, they have now battery factory. This is very good news for us. So I hope the government can also still keep encourage and support the Indonesian scientists. Okay, thank you very much for listening. I hope you can enjoy my presentation, and we can exchange ideas. Once again, thank you very much.
Okay, you're welcome, Dr. Al-Faruqi. It was very interesting topic. Okay, we are moving for the question and answer session. We have 15 minutes for this session. If you have question, please raise your hand or type in chat box and I will read it for you. Please. Please raise your hand. No? I have a question for Dr. Al-Faruqi. So you were talking about cathode, and how about the research on anode in your laboratory and prospect for Indonesia? Is there any challenge for developing an anode?
Okay, it's very interesting question. Basically, in our lab, we also works on the anode materials. It involves, for example, carbon-based materials. For example, the graphite, and also we work on the transition metal oxide anode materials, as well as the silicon-based. So basically, as you can see here, how to increase the energy density of lithium-ion battery. Basically, if we trace back from the development of the first generation, from Professor Whittingham, 1976, they tested the battery using lithium metal, basically using lithium metal, and because of the dendritic problems, because it compromised the safety, so they developed the graphite, for the anode after the realization of lithium intercalation into graphite. So after this, they used graphite, but they varied the cathode materials. They use NCM, they use LFP, for example, and other cathode materials. But the energy density that can reach like 250 watt-hour per kilogram. And Tesla also started like making nanocomposites, for example, the carbon-based and silicon-based materials for the anode. Yeah, so it can basically improve a little bit, the energy density of the lithium ion batteries. And if they use full silicon, silicon anode, for example, yeah, there's one also company in US founded by Professor Ichui of the Stanford University. So they developed this kind of silicon nanowire technology, yeah, as the anode. And then finally, they also moved, yeah, they return back to lithium metal, but it should be highlighted that if we use lithium metal, we need also to consider many aspects. Yeah, for example, the separator, the cell design, and many things we need to consider about it. Of course, it can increase the energy density. And finally, lithium metal sulfur. Yeah, and if you ask about the Indonesia about this anode, yeah, of course, Indonesia also has potential to develop this carbon-based as well as the silicon-based anode, as well as the transition metal oxide-based anode. Yeah, so Indonesia still have good chance also for that. Also for sodium. For sodium, now the promising ones, they use the carbon-based anode, the hard carbon. So Indonesia still has also a good opportunity to involve, yeah, in this anode-based research and development.
Okay, thank you very much. Please, if you have any more questions, we still have 2 or 3 questions. Please raise your hand or type it in chat box. So may I conclude that, may I conclude that the research in cathode is more challenging than research on anode, isn't it?
Because I think, yeah, based on our discussion also with other researchers, it kind of almost hit the wall. Okay, research on the cathode almost hit the wall. It's kind of very difficult to improve more. Yeah. So, for example, we add more nickel, but there's some limitation. We cannot use all nickel. For example, only nickel oxide. So there's more limitation for that. So after some variation of the concentration, nickel, cobalt, manganese, for example, or nickel, cobalt, aluminum, there's some already, they almost reach that kind of energy density. Yeah. So that's why how to increase more, people now also started to doing some research about the anode side also. Yeah. But we need to understand there's some parts, yeah, anode, cathode, but we need to also consider also the electrolyte. This also plays a very important role. Yeah. So yeah, well, if you say, for example, it's more difficult, yeah, we can say because it's already reached some limitation and people not so many record, yeah, because they already reach some certain level. So after, for example, they got the best composition for the cathode materials, they can use same cathode materials, for example, but they also alter the electrolyte, for example, little bit. They add some additive, something like that, so it can improve the cycle life, for example. Yeah.
Okay, thank you very much. We still have one more question. If any of you can give question, please raise your hand or you can directly unmute yourself. Hello? If so, I would like to say thank you for Dr. Al-Faruqi on behalf of ICIMECE 2021 committee. we would like to thank you for joining us today. Thank you for.
Pleasure.
Okay. We can move to the next presenter. I would like to welcome Professor Anita Pettersson from University of Borås, Sweden. She will be speaking to us on circular phosphorus from sewage sludge by combustion or pyrolysis. Before that, let me read a short profile of Professor Pettersson. Professor Pettersson is working as senior lecturer and researcher within the area of research, recovery, thermal treatment with focus on waste and biomaterial, in addition to material recovery, as for example, from waste and incineration ash. She has been working at University of Borås since 2008. Before she did her bachelor on science in electrical power and heat at University of Borås, and her PhD was issued from Chalmers Technical University in cooperation with University of Borås. She is a member of Combustion and Thermal Process Research Group, University of Borås. The goal of this research group are to optimize the efficiency and economic of heat and power plant, at the same time to minimize the usage of the natural resources and the environmental impact. I would like to give the floor to Professor Pettersson. Please, you have 30 minutes to present, Professor.
Thank you very much, Dr. Budiman. I will try to share my presentation here. Oh. Is it okay?
Yeah, it's clear enough.
Perfect. So thank you very much. And I would like to thank the committee for the 7th International Conference in Industrial, Mechanical and Chemical Engineering for inviting me as a speaker. It is an honor. I've been to Indonesia several times, so I'm not so sure that I chose the right topic for this conference now when I've thought about it. Maybe waste to energy would have been a better topic. However, this is one of the research areas which I'm working in, and it's very important for the future. So that's why I chose phosphorus recycling. I would like to start with to introduce our research group. We are called the Swedish Center for Resource Recovery, and you can look more on our homepage following this link here. We are taking a lot of different waste stream and try to upgrade them to something useful. And everything we do in our research is to come more close to a sustainable society. We have about 25 PhD students in the group for now. And in the part of thermal treatment where I work, we have about 5 PhD students. And we are 3 senior lecturers and 1 postdoc. So we are, as I said, trying to make use of what we otherwise would think of as waste. And that is something we have to improve a lot in the future to have this sustainable society that we would like to have. In my presentation today, I would like to start with some background, co-combustion tests, results, and then conclusions, and then I will show pyrolysis and some results and conclusions. So the background, why is it so important to recycle the phosphorus from the environment? Yes, phosphorus is a limited resource. It's crucial for the world's food production and also in the metabolism of every living creature, such as the human being. We can't live without phosphorus. And as I said, it's a limited resource. The phosphorus that we utilize today is approximately used to 90% as fertilizers. The European Union had put it on its list of critical raw materials. And the recycling is very limited today. Almost no phosphorus is recycled. If we look at the mining reserves, Morocco is the country sitting on the biggest reserves, 75%. But the researchers are fighting over how big these resources are in reality, because the phosphorus that is mined is becoming more and more contaminated with all kinds of different heavy metals and radioactive material, which make it much harder to use and also not so environmental friendly or friendly for the users. If we look at EU, Finland is the only country which has their own mine, and as the regulations is today, all phosphorus that is used in the Nordic countries comes from this mine, because that's the cleanest mine in the world. And yeah, it's very expensive to clean the phosphorus from these contaminants. So that's why we use this phosphorus from Finland. So here you can see the phosphorus cycle as it is today. We have the mines, which are mostly open pit. We take out the phosphorus and we upgrade it to fertilizers. The fertilizers are used for the crops. Either this crop is eaten by animals or by us and processed in the metabolism. If we then eat the animals, or if we eat the green vegetables directly, all the phosphorus will end up in our stomach, and it will go the natural way and will be collected in the wastewater treatment plant. I have looked at Indonesia, and you have wastewater treatment plant, at least in the bigger cities. I think there are much more to do to clean the water maybe, but there are potential at least, because in this wastewater treatment plant, we take out the sewage sludge, and to keep the phosphorus or to prevent the phosphorus to come out in the waters, we take it from the wastewater here and precipitate it, and then it's collected in the sewage sludge. And here you can see a picture of dewatered sewage sludge. It's common in many places today that this sewage sludge goes directly back as fertilizer, because it contains a lot of phosphorus. It is in the same region as this phosphorus ore. However, we have a lot of other contaminants here as well. So we are not so keen on taking this sewage sludge back directly, because it contains microplastics. It contains different medicals and hormones. It contains dioxins and other pesticides, and it also contains a lot of heavy metals. And all this is coming from the wastewater. So when we take this sewage slide directly as a fertilizer, we also risk to contaminate this land. And that could be a crisis in the future. If we look at the sewage sludge utilization in EU, I'm sorry, these are a bit old, but I couldn't find any more recent. However, we can see that 51% was going for agriculture. That means direct use back. 25% for incineration. And my guess is that in incineration, we both have what we call incineration. We just combust it to destroy the material, but also a waste to energy, so that we take back some of the energy, producing electricity and heat and so on. Landfilling, compost or other. And yeah, this will not be sustainable to treat the sewage sludge like this. We must come up with new ways to treat it, and also to make sure that clean phosphorus comes back to the farmland. So in my research, our goal is to take this sewage sludge, make it into ash, which is phosphorus rich, or make it into a char, which also is phosphorus rich. And by that, destroy all these organic pollutants, and hopefully also get rid of some of the heavy metals. So if we look at we start to look at the way of treating the ash or making the ash, we have co-combustion, which is most common in Sweden. If we look at Germany, they often have a monocombustion, only combusting sewage sludge. Then we have a lot of problem with this water. We have to have some pre-drying and so on. But by co-combustion, we will not have to do that. We can have a pretty dry fuel anyway. Then we have our combined heat and power plants, where we do the combustion. We come up with an ash without these organic pollutants, and hopefully not so much heavy metals. If this ash is clean enough, we can use it directly as a fertilizer and maybe a soil improver. And if it's more contaminated, yes, then we at least have enriched the phosphorus here, and we can take it out and make new fertilizers from it. So co-combustion of municipal sewage sludge with biomass for direct use of ash as fertilizer. It would destroy the organic pollutants, as I said, pharmaceutical residues, microplastic, dioxins, and all other organic pollutants we can find here. It would volatilize heavy metals to the flue gas, and we can collect it in the fly ash in the flue gas cleaning system. And we can retain the phosphorus in the bottom ash. So instead of this cycle here, we would like to take this sewage sludge and make it to a fertilizer, a clean fertilizer, before we use it on the farmland. What is new in this research? Yes, some research has already been done, but it has mostly been done in fluidized bed, or only in fluidized bed combustors. And we are looking at a grate boiler instead. Why? Yes, because then the temperature would be higher, and it would be hopefully easier to volatilize the heavy metals, which is crucial. No bed material would be involved, because in a fluidized bed, most often you use extra sand to get this fluidization that is wanted. And then the sand is mixed up with the bottom ash, and we don't have a clean ash fraction to take. So here we have just focused on grate fire boilers. The performance then, we had three cases. We of course started this research in lab scale, and we have a small lab scale reactor at the university. And we also used the TGA for the startup research. However, the results I will show you today was in a full scale boiler used for production of heat and power. And this boiler is usually fed by demolition wood. So the first case, the reference case, was 100% demolition wood. And the second case was 50% sewage sludge and 85% demolition wood. And the third case was 30% sewage sludge and 60% demolition wood. And here we didn't change the moisture content much in the boiler. So it was within the designed content for the performance of this boiler. The sewage sludge we used was pre-dried, because we have a dryer in Sweden where you can take the sewage sludge and you can just dry it by heated air, and the air comes from a wood pellets boiler, and it heats oil that then heats this big oven here. This sewage sludge was not used for anaerobic digestion, so it was raw sludge coming directly from the wastewater treatment plant. Here you can see a picture when we had mixed this demolition wood with the sewage sludge. And we used a dumper to do that. If we look at the composition of the different fuels, we can see the demolition wood here in the first column, then the clean sewage sludge, and then the mixes. What we discovered when we were starting this research was that the demolition wood was much more contaminated than we knew from the beginning, because other research have been done with demolition wood, and of course the quality is varying. But in this case, we had high concentrations of some of the heavy metals that we were not so happy to have, as cadmium, for instance, was really high concentrations. Also lead was very high, and arsenic. And zinc was higher compared to the sewage sludge, which is not so common either. But this zinc here probably originates from white paint. So that was not so good results when we had this analysis of the intended fuels. However, then it was too late to do anything, so we had to go through with this research. Here we can see the feeding and the mix with the sewage sludge and demolition wood. And here we can see sampling. So we took out the ashes, the bottom ashes, just before they otherwise would fall down in a water bath. But we didn't want to have this ash reacting with the water. So we took it directly in the front before it fell down inside the boiler. And we had a special spoon designed for this. And this is one of the workers. He did this very well, so you could think that he did this every day, even if it was the first time. This is how it looks from inside. So the hole you can see here in this picture is the same as this one here. And I'm taking this picture from exactly the same hole on the opposite side of the end of the boiler. So here the fuel is fed from this side and slowly moving in this great fire boiler. So here is the front of the bottom ash. So here all material should be burned out. And then it was falling down on this hatch. And this hatch was opening, I don't remember how often now, but it opened and let some of the ash down to the water bath. So were collecting, as you can see here is the spoon coming in. We were collecting the bottom ash here just before it was falling down. here you can see the spoon into. And we tried to take samples. We could not, of course, come to the other side of the boiler, but here we tried to take samples from the middle and out in the wall of the boiler to get a mixed sample. We also did FTIR measurements on the flue gases, because just to look at the gas analysis in the end of the boiler is not very informative when we do this type of research. We need to know what we have in the gases in the boiler before the flue gas cleaning system. And that's why we use the FTIR. We also took deposit sampling here. So to see what the deposits that was formed in the boiler and could be stuck on the tubes. So in this probe here, or on this probe, we had these steel rings and the same quality as the tubes, the superheated tubes in the boiler. And we had some different surface temperatures here to investigate the different impact on the surface temperature of these tubes. However, I will not show these results in this presentation today. That will be a later presentation maybe. So some results. If we look here, we can see that here we have only demolition wood. We have the bottom ash and we have the fly ash. Then we have the case with 15% sewage sludge, bottom ash and fly ash. And then we have 30% sewage sludge, bottom ash and fly ash. Sorry. And we have aluminium in the blue columns, zinc in the orange, and phosphorus in the green ones. So we can see when we have only demolition wood, we have a very low concentration of phosphorus here. And also aluminium is a bit lower compared to the others, and zinc. More zinc is collected in the fly ash compared to the bottom ash, and less phosphorus and less aluminium. When we add the sewage sludge, we also increase the amount of aluminium, and that's because aluminium was used as a precipitator of the phosphorus in the wastewater cleaning plant. And there is different chemicals used and sometimes also biological processes. But in this case, this sewage sludge we used here was precipitated with an aluminium sulfate. If we look at the zinc, we can see that we had a little higher zinc in this case, probably coming from the demolition wood, because in the case with higher amount of sewage sludge, it was lower again. And if we look at the phosphorus, we can see that most of the phosphorus was collected in the bottom ash. We also had some in the fly ash, but the biggest amount was collected here, which was good. Then we can look at the results for some of the heavy metals. And if we look at the first here, where we have only demolition wood, we can see that we have high concentration of chromium. We also have pretty high on nickel. And arsenic is also pretty high compared to those with sewage sludge. The only problem here actually with adding the sewage sludge was the lead. And we are not totally clear of why the lead was increasing, especially here in the fly ash. It was not a big problem in the bottom ash, maybe in this case here. But when we talk about the 30% sewage sludge, it looked okay. However, we were a bit worried about that. and also the arsenic in the fly ash especially. Here we can see that we have, here in this graph, we are showing the 15% sewage sludge bottom ash and the 30% sewage sludge bottom ash, compared to the Swedish regulation for how much sewage sludge, clean or raw sewage sludge you can put on farmland. And you also how much this sewage sludge, which we used in the combustion tests, contain. And then we can see how much we could find in the fuel mixes. So we can see that the fuel mixes contained a lot of arsenic here. Also pretty high cadmium compared to the rest. And mercury was not a problem here. But this also shows that this cadmium and arsenic comes from the demolition wood. So with a much more clean forest fuel, for instance, we could have an outcome here that was much more suitable. If we look here, we can see here we compare to 1 milligram per kilo phosphorus, and it's the same. We have the bottom ash from the 15% and from the 30%. We have the Swedish regulations. We have the sewage sludge, and we have the fuel mixes. And here we can also see that zinc is really high in the fuel mixes. Lead is pretty high compared to the legislations anyway. Chromium and nickel is also a bit too high. And if we look at the concentrations in the fuel, we can also see that chromium, lead, and zinc here comes from the demolition wood, which also shows that if we had chosen a much more clean fuel, we wouldn't have these problems. So the conclusions were mercury and cadmium are volatilized, and the bottom ash is rich in phosphorus. And P will be, it will be low in mercury and cadmium. Less volatilized metals, especially chrome, nickel, and copper, will be, they will just be volatilized to a smaller extent. Depending on the content of arsenic, chrome, nickel, and copper, and lead in the base fuel, the demolition wood in this case limits in the relation to the REVAC, which is the Swedish regulations for arsenic, chrome, nickel, copper, and lead, could be exceeded in the future. Even arsenic and zinc, despite the fact that both are volatilized to a large extent, could end up in the bottom ash together with P in too high levels. So that's a risk, especially with this co-fuel. However, with a clean base fuel, it looks very promising. So the results were very good for this. However, yeah, and I would like to thank Umeå University, Njudung Energi, where we did this research, RISE in Sweden, Mora Vatten, who delivered the municipal sewage sludge, and Borås Energy for their help. And then we were funded from the resource by Vinnova, Energimyndigheten, and Formas in Sweden. So now I will go to our ongoing research, and that is paralyzing of sewage sludge. So then we take the sewage sludge, and instead of an ash, we make a char. What is the benefits with this? Yes, then we keep most of the carbon here, and we will have a much better soil improver. than just with the ash, because the char is carbon and P-rich ash. So it will be more or less the same ash as before, but also with this carbon. We have done these tests with the 3 different municipal solid sludges and sewage sludges, and I will present 2 of them here. This research has just been done in lab, but in a pretty big rotary paralyzer, which you can see here in this picture. So the sewage sludge is fed here, and this feeding system is closed, of course, because we want to have paralyzers here, no air coming in. And out in this end, we get the char. And the heavy metals are following the flue gas system here, are combusted with the gases here and collected in the flue gas cleaning system, together with the dioxins, if any is produced. So instead of having, as I said, the ash here, we would like to have a char. And also here, it's also possible to make or take out the clean phosphorus from this char if needed. But here we have a better material for soil improvement. This is the lab rig we have. We have a nitrogen atmosphere. So nitrogen is continuously added into this system together with the sewage sludge. We have a rotary paralysis, as I said, and we are doing tests at different temperatures, 500, 700, and 900 degrees. The material is added here, and it travels slowly through this rotary kiln. The product gases are coming out here and are combusted because today we can't take care of those gases. We use a LPG or cosan gas to have a flame here all the time to make sure that the gases is properly combusted. And then we monitor the flue gas concentrations by a tester sensor in the end here, where we can monitor Cu, CO2, oxygen, laughing gas, and NOx. Yeah. So we are monitoring that all the time. Here is when we are emptying, because we have a continuous feed, but we can't empty it yet continuously. So we feed it for a while, we let it paralyze, and then we cool it down and we empty the paralyzed material like this. So some results from this. We had so low concentration of arsenic and cadmium that we couldn't analyze them with the equipment we have. And if we look at the rest here, we can see that the blue one is 500, orange is 700, gray is 900, and the raw sludge is the yellow columns here. So we can see that these elements are enriched in the char compared to the original raw sewage sludge. And if we recalculate it as kilo per sludge instead inserted to the boiler, then we can see that magnesium, zinc is the same or less than in the sewage sludge. Also copper is more or less the same. Lead is the same when we come to 500, and so is chromium. And nickel is a little higher for 500, but not so much. We have most for 900, which probably is because we have some leakage from the steel at these high temperatures. If we look at the phosphorus, iron, manganese, calcium, potassium, and sodium, and the milligram per kilo char, we can see also here that we have enriched the phosphorus and the iron. Magnesium is more or less the same. Calcium, we have some changes, but not so much. A little higher for potassium, and sodium has actually decreased a bit. If we recalculate it as milligram per kilo of sludge, we can see that for phosphorus, we have kept the phosphorus we added, the same with the iron. We have lost some of the magnesium, and we have lost approximately half of the calcium, a little of the potassium, and a lot of the sodium here in the process. This means that if we compare these different temperatures, in most cases, actually 500 would be the most proper temperature. That was not what we thought when we started. We thought that higher temperature would give us better results for the metals. However, the results we have so far shows that actually the lower temperature would be more preferable. Also, if we look at the remaining energy value, which also could be referred to how much carbon is left, we can also see that in this case is the Mora sewage sludge. It started raw sludge with about 19,000, now I don't have, but it should be megajoule per kilo, I think. And it has decreased to 15 here. Here, the difference between the different temperatures is not very big. So it doesn't matter so much, but it's a little bit higher, of course, at the lower temperature. If we instead look at the Lidköping sewage sludge, we can see that here we start a little lower compared to the Mora sludge, but we can also see that the temperature is a little more, doing a little more difference here between the temperatures. And here 500 degrees would be the most preferable, where we have lost the less of the carbon. So all these results shows that 500 degree would be a proper temperature to use here. So the conclusion is that most phosphorus is captured in the char. Some metals are accumulated, some are reduced. The energy content is not affected much because of the temperatures. The high energy content means high carbon content. This could be a good sewage sludge treatment for the future, improving food production and soil quality. And with that, I would like to thank you for this time which I was given in this conference, and I hope that you found this research interesting. Thank you very much.
Thank you very much, Professor Peterson, for a nice presentation. So let's move to the question and answer session. If you have question, please raise your hand or type it in the chat box. Actually, I have some experiences for the research on water treatment, Professor. So the problem was I cannot get the standard quality of the waste. That's why if we collect from other location, the quality of waste will be much different. So how do you make your research to get the conclusion that method could be a good method to perform the post-porous recovery, even though the quality of waste will be vary based on different location.
Yes, that's why we have chosen 3 different sewage sludge in Sweden, because they have different quality and also they are pre-treated in different ways. The last which we are working on now is sewage sludge, which is first going through a biogas process. So we already lost some of the carbon from that one. Also, the metal contents in all these 3 sewage sludges are varying, of course. So that's why we picked them to see if this process could be suitable for different. But if we have in some places sewage sludge which is outstanding, you could say. In Falun, for instance, where we have old mining industry, we have a lot of heavy metals in the sewage sludge from the wastewater treatment plant. So that sewage sludge is especially problematic, and I would say that I don't think it would be interesting for this type of a process. But if we look generally of the sewage sludge we have, it's very good. And if you have a proper phosphorus capture in the wastewater treatment plant, the concentration of phosphorus would be almost the same in all sewage sludges. And so that is not varying between different plants, not much anyway.
Thank you. Any other question, please? Okay, I received question directly. So, talking about environmental protection, Professor, we need to consider the energy release for this process. As we know, your process is contains some drying process and also pyrolysis process. That means the energy release is so much. Do you consider how much energy release for this process, and will it be good for the high scale implementation for sewage treatment processing, Professor?
Yes, because we have a product gas that is produced here, we can use that gas back and use that for both the drying and for the process. In our lab scale, of course, we have electrical heating, but we are planning to build a pilot plant now in the south of Sweden, and then it would be suitable to use this product gas. Of course, we need to add energy in the startup, and maybe also depending on the input, how wet the sewage sludge is. Might be, you might need to have some extra energy, but much of the energy consumption could be by the product gas itself.
I see. I get the point. Thank you very much, Professor.
And also, if we compare sewage sludge pyrolysis with the wood pyrolysis, for instance, we don't get much oil or what is called char in this process. We get the char, not char. What is called? Also sticky. Tar, yes.
Tar.
So we get the char and we get the gas, and not much in between. So it's a very clean process if we compare it to when we pyrolyze wood materials. And also that also shows that more of these combustibles are found in the gas directly, because we don't have this tar or oil production.
So only gas, solid material.
Yes.
Thank you. Any other question, please? Okay. Maybe we can close this session. Thank you very much, Professor Peterson, for a nice discussion. So we would like to again thank you for joining us today, for your time, for our invited speaker. We are also thanks for all participants. Thank you for all the committee and also the engineering faculty of Universitas 11 Maret. So please, we can return to the main session for the taking an information of award announcement. As a moderator today, I would like to thank all and see you for the next occasion. Thank you very much, Professor Peterson, Dr. Al-Faruqi, and other participants. Thank you.
Thank you very much. Thank you.